Let's continue with ZEUS training, section 6, automated mesh generation. So there are generally two steps involved in generating a mesh system for executing ZEUS. We have the surface mesh generation and the flow field mesh generation. Now ZEUS solves the Euler equation on the flow field mesh, whereas the surface mesh is used only as a reference mesh for the automated mesh generation scheme to generate the flow field mesh. The automated mesh generation scheme may create extra grid lines on the surface mesh, and after the solution is obtained on the flow field mesh, ZEUS then interpolates the solution from the flow field mesh to the surface mesh so that the final solution is always presented on the surface mesh. Now, similar to ZEUS, the surface mesh is defined by two bulk data cards, the ZEUS 7 bulk data card for Winglike Components and the Body 7 bulk data card for Bodylike Components. And then to assist with the flow field mesh generation, ZEUS also has gap cards. We have the gap, gap 1, and gap Z. For purposes of the mesh generation, they function similar to the ZEUS 7 in that they direct the flow field mesh grid lines where they should be generated. However, the gap cards are kind of fictitious in that of course, they don't exist in the actual surface panel of the model. They're only for the mesh generation. So the ZEUS 7 and Body 7 are the only cards that have surface panels that make up the aircraft. Now, once the surface mesh is defined, then ZEUS can automatically generate a block of flow field mesh by growing the mesh from the surface mesh. And simple models such as a fuselage, wing, and horizontal tail can usually be fitted into a single block of flow field mesh. And for complex configurations, such as aircraft with stores, multiple blocks of flow field mesh are required to generate an overset mesh system. So we'll go over the surface mesh input here. To establish a ZEUS surface mesh for an aircraft configuration, the first step is to divide the configuration into winglike and bodylike components. The winglike components are the lifting surfaces whose spanwise cross sections can be represented by an airfoil-like thickness distribution. And these types of components include wings, tails, fins, pylons, and launchers. And then the bodylike components are the non-lifting types of body, such as the fuselage, nacelles, missile bodies, and stores. Now, ZEUS inherently assumes the flow direction is at 0-degree angle of attack to be along the x-axis of the global aerodynamic coordinates. That is, the flow flows along the x-axis. So the fuselage must be located along the x-axis, and the canopy from the pilot's point of view must be located towards the positive z-axis. So positive z is up, and then positive y is along the right-hand side wing, and then positive x is aft, pointing aft. So if a half-span model, if you only model a half-span model, then the model must be located on the positive y-axis, as shown in the figure. So first we'll talk about the winglike components. The winglike components are defined by the ZEUS 7 bulk data card. And each ZEUS 7 defines a trapezoidal flat sheet of surface of which the inboard and outboard edges are parallel to the x-axis. And the thickness distribution of the winglike component is defined by the PA foil 7 or PA foil 8 bulk data card, which does not affect the position of the flat sheet of surface. The trapezoidal flat sheet of the surface is further divided into several spanwise and chordwise divisions in order to establish the surface mesh of the lifting surface. So the flat sheet of surface mesh is fitted into the flow field mesh, as shown here in the top-down view, and the volume mesh does not model the wing thickness. The thickness effects are applied on the flat sheet of the surface mesh using the transpiration boundary condition. And then the volume mesh is automatically generated by growing vertically from the surface mesh. So if you're familiar with Nashtran and you want to model a control surface, most often in Nashtran, if this was the control surface, the outer 3 spanwise panels and then the aft 2 chordwise boxes, this would be its own C arrow, then you would have a second C arrow forward of that, and then you'd have a third C arrow on the inboard section. ZEUS, you cannot model like that. The entire wing from the leading edge to the trailing edge must be one C arrow 7. You can optionally split the wing in the spanwise direction into multiple C arrow 7s. So you could have these inner 2 panels be one C arrow 7, and then the outer 3 panels be a second C arrow 7. But if your overall shape is a trapezoid, the easiest thing to do is just use one C arrow 7, and that would be recommended. The reason that you can't split the wing into multiple C arrow 7s going from the leading edge to the trailing edge is because you need to use the PI foil 7 to define the wing thickness, and you cannot have two C arrow 7s, one right behind the other, with the PI foil 7 to model the wing thickness. That's just not allowed in ZEUS. Okay, moving on to the Bodylike components. The Bodylike component is defined by specifying a body 7 bulk data card that further refers to a seg mesh bulk data card on which the surface grid points of the body are specified. And the boundary condition of the body is applied on a box-like prismatic surface that embodies the actual surface of the body. Now, ZEUS employs a correction parameter derived from a slender body theory to account for the spatial difference between the prismatic and the actual surfaces. And the Cartesian mesh is automatically generated by growing from the box-like prismatic surface. So in this figure, we can see the surface panel modeled here. The box-like prismatic surface is actually the box here that encompasses the body. So computationally, the body is represented by this box here. And then the 3D mesh is grown off of the box, so you can see how the Cartesian grid grows away from the box. And then in the XZ plane, so our top-down view, you can also see the box right here. And then the mesh is grown away from the box out on the right and left-hand sides here. Now, the strategy of modeling the body surface by a rectangular box actually works surprisingly well, and it's validated by the good agreement between ZEUS solution and an Euler solution with the exact boundary condition along a hemisphere cylinder body at an angle of attack of 5 degrees and Mach 0.9. So our ZEUS solution is in red here, and then the exact Euler solution is the blue circles. So if we look at the CP here on where psi is 0 degrees, so this would be on the right hand side, and then this is the upper surface, and then this is the left hand surface. So you can see that the ZEUS matches quite well with the exact boundary condition. Note that the user doesn't have to model this box explicitly, and we'll see that later. You just need to input the surface panel model, and then ZEUS will determine where that box goes, and then automatically grow the mesh off of that. So next, we'll look at how ZEUS generates the block of the volume mesh. The volume mesh is generated by the block bulk data card. This specifies the outer boundary of the block as shown in figure A here. So the user specifies what the outer boundary of this block is, and then it defines the Y zones for the automated mesh generation, and it refers to the C arrow 7 and body 7 bulk data cards that are fitted into the volume mesh. So if we look at this top-down view, this global block of mesh is referring to all of these C arrow 7s that make up the wing and winglets, and then the body 7. And then you can see that the mesh grows off of the surface panel model to generate the 3D volume mesh. Now additionally, we have the gap 1, and gap Z bulk data cards to refine the volume mesh. So in this example, it looks like we've used some gap cards both in front of and behind the wing to assist the mesh generation. This is usually required when you have a wing and a fuselage in the same block. So it just helps have a smoother mesh in front of and behind the wing. And default values of parameters to control the growth rate from the surface mesh can be altered by the mesh param bulk data card. And the volume mesh is generated in a local coordinate system specified by the ACORD bulk data card. In this example, the global block, the mesh doesn't need to be in a local coordinate system. But if we had some engine pylons out here or underneath the wing, then you might need a local coordinate system for that particular block for the overset scheme. So next we'll look at the mesh projected on the XY plane. Now this, how ZEUS generates the mesh is important for the user to understand so that as they're trying to create a good mesh, they'll know where to look. For example, when you might need to add a gap card to your model to help ZEUS create a better mesh, or how you should distribute the cuts in your body 7 or your C-Arrow 7 to ensure that you have a good mesh. So it's good to know what ZEUS is doing behind the scenes. So first, for this mesh projected on the XY plane, if we look at the chordwise Y lines, which are highlighted in black here, the line runs from the left wing to the right wing at each X station. Now if the wing is unswept, then the chordwise Y line is parallel to the Y axis. And we can see that right here with the body, where the Y line in this particular region is parallel to the Y axis. However, the chordwise Y line can be sheared to accommodate the sweep angle of the wing leading and trailing edges. So we see that here, where due to the wing sweep angle, this Y line has been sheared. And then if we look at the Spanwise X lines, the line runs from the upstream to the downstream at each spanwise location, and the Spanwise X lines are normally parallel to the X axis. However, it can be sheared to accommodate the variation of the body width along the streamwise direction. And this is kind of an advanced option. Usually, you don't need to shear the X lines here. We can just leave the prismatic box as being a straight box where all of the X lines are parallel to the X axis. But for smooth bodies like this, you can specify in the body card and the seg mesh card, you can tell ZEUS that I want these X lines sheared. So you can see that these are sheared quite a bit, and then gradually as we move out, they become sheared less and less until at a user specified location, the X lines become parallel to the X axis once again. So usually the shearing does not need to happen, but you can turn it on if you would like. So the mesh on the XY plane is invariant at the different Z stations because all of the vertical lines in the 3D mesh are parallel to the Z axis. So if we look at different Z slices of the mesh, we're going to see the same XY grid at every Z station because all of the Z lines are parallel to the Z axis. There is one exception to that using the block T, but we'll talk about that later. Next we have the mesh projected on the YZ plane. So the horizontal Y lines are shown here. The line runs from the left wing to the right wing at each Z station, and if the wing has no dihedral angle, then the horizontal Y line is parallel to the Y axis. However, the horizontal Y line can be sheared to accommodate the dihedral angle of the wing. So in this example, when we get out, the wing has slight dihedral, and then when we get out to the winglet, we have very severe dihedral. This is actually poor modeling. With this large of a dihedral angle in the winglet, you would actually want to put the winglet in a different block and use the overset block scheme. But for illustration purposes, we just have one block here. So you can see how that the horizontal Y lines have been sheared, not only along the moderate dihedral angle here, but then even the severe dihedral angle with the winglet here. Then the spanwise Z lines. These lines run from the bottom to the top of each spanwise location, and the spanwise Z line is always parallel to the Z axis. And the mesh on the YZ plane could be varying at each X station because the sheared Spanwise X lines on the XY plane. And then next we'll look at the mesh projected on the XZ plane. So this is the side view. The horizontal X lines normally are parallel to the X-axis. So here we run from the upstream to downstream at each Z station. The horizontal X line is normally parallel to the X-axis. However, optionally, it can be sheared to accommodate the variation of the height of the body along the streamwise direction. So this shearing only occurs for body elements. It does not occur for the ZEUS elements. And then once again, this is optional, and you usually don't need to do this, but the option is available. Then we have the chordwise Z lines. These lines run from the bottom to the top of each X station, and they are parallel to the Z axis. And the mesh on the XZ plane could be varying at each span station because of the sheared chordwise Y lines on the XY plane. So next we'll review the YZone technique for the automated mesh generation. So here we've have a top-down view, so we're looking at the XY plane, and we have a body element here of the fuselage, and then we have several ZEUS making up the strake, wing, horizontal tail, and launcher. So here all of the components within each block are projected on an XY plane. On this XY plane, all of the components are divided into several spanwise zones called Y-zones, and the user is responsible for specifying the boundaries of these Y-zones. So we'll look at where you choose to put these Y-zones. And the YZone technique can automatically generate the mesh on the XY plane by a line tracing method that connects the chordwise Y lines across all of the Y-zones. So within zone 2 here, this Y-zone, ZEUS will look at this ZEUS and then any gap cards that you may have which are not displayed, and it will create all of the XY lines following this ZEUS, and then in front of and behind the ZEUS, it will grow those lines out. Then in adjacent zones, we do the same thing. So the same line tracing method is also applied on the mesh projected on the YZ plane to connect the horizontal Y lines from the adjacent Y zone. And then the YZone technique enables the generation of the sheared mesh on the XY plane to accommodate the sweep angle of the Winglike components, and a sheared mesh on the YZ plane to accommodate the dihedral angle of the Winglike components. So after we do each Y-zone, then ZEUS just connects the Y-zones to each other, so we have one YZ line running all the way from the left to the right. So where we want to break up these Y-zones, you can see that whenever we have two different ZEUS, you want to place those into a different Y-zone. So we have the launcher in a Y-zone, and then this one ZEUS making up the wing, we've actually split it up into two different Y-zones because of the horizontal tail. So at the horizontal tail boundary, we have a Y-zone boundary, and we want to make sure that we have a cut, a spanwise cut in the ZEUS that aligns with the spanwise cut of the tail. So this cut is aligned, and this restriction is the same as ZEUS, but for a different reason. But we can see we have an aligned cut here, and then each of these inner cuts of the ZEUS and horizontal tail are also aligned. So we have this Y-zone, Y-zone 2, which has the outer wing, then Y-zone 3 has the inner wing and the outer portion of the horizontal tail. Zone 4 has the inner portion of the ZEUS making up the horizontal tail, and then this strake element here. Zone 5 is this single strake element running from the leading edge of the wing to the trailing edge of the tail. Then we have Zone 6 is the fuselage, and then Zone 7 through 11 are mirror images of Zones 1 through 5. Notice that we always go from left to right in ZEUS. So for the ZEUS, each individual ZEUS, we define the root side of the ZEUS to be the left side, and the tip side of the ZEUS to be the right-hand side. And then our zones go from left to right. So we'll look here at the sheared mesh on the XY plane between two adjacent Y zones. The YZone technique first generates a set of chordwise Y lines in each Y zone on the surface mesh. So here's a coherent mesh between two C07s. So we have a C07 here with 3 boxes, and then we have a C07 here with 3 boxes. So both of them have 4 cuts, and the cuts align with each other. Now, based on the chordwise divisions of the C07 bulk data card and the axial stations of the body 7 bulk data card, we generate these lines. And each chordwise cut of the surface mesh generates a chordwise Y line, shown here by the arrows. And then the connection of the chordwise Y lines between adjacent Y zones is achieved by the line tracing method. So what you want is obviously these lines to connect to each other. So the cuts in this C07 align with the cuts of this C07, so we have coherent mesh lines. Now if we go over here on the right hand side, where we have a non-coherent mesh between the two C07s, we have these 2 inner cuts of the C07 are here, but then on the outer board C07, the 2 cuts are out here. So what will happen is this instant is ZEUS will generate a chordwise Y line right here aligned with this cut of the C07, and then it will come through here. So our computational mesh will have a line at the leading edge, and then it will have a second line here aligned with this cut of this C07. It will have a third line here aligned with this cut of the C07 and then going through this Y zone. A fourth line here aligned with this C07 and then going through here. And then a fifth line here, and then finally a sixth line at the trailing edge. So what we've done here is we've increased the number of computational volume cells in our grid because of the non-coherent cuts in the C07s. So this will increase your computational time because we now have more computational boxes. And then when ZEUS goes and interpolates the flow solution back onto the C07, we lose the fidelity of the increased grid density because our mesh size, we only have 1, 2, 3 panels, whereas we had 1, 2, 3, 4, 5 boxes. So we're needlessly doing extra computation in ZEUS for no really net gain in our solution accuracy. So what you want to do is have the lines line up. So now we only have the 3 boxes. Or if you want, the increased mesh density, you could add extra cuts to your C07. So the extra chordwise Y lines are generated, shown by the dashed lines, if the surface meshes between the 2 macro elements are non-coherent. And these extra lines can adversely affect the smoothness of the mesh. As you can see here, we have a really big box and then a really small box. And also increase the computational time because we have more computational boxes. And then it's highly recommended that all adjacent micro elements, either between 2 C07s or a C07 and a body 7, have a coherent surface mesh at their juncture. The one exception to this rule that I use in my modeling, if I have a C07 here, and let's say it has 40 boxes, so we've got a pretty fine mesh. In the fuselage, I don't want to bother modeling 40 chordwise boxes from the wing leading edge to the wing trailing edge. That's just it's just too many boxes and it's more modeling effort. So what I'll do instead is just have 20, for example, or maybe even 10 boxes from the leading edge of the wing to the trailing edge of the wing. But I'll still make sure that those cuts, those 10 or those 20 cuts, perfectly align with the cuts that I have in my wing. It's just that the extra cuts in the wing will go ahead and cut through the body. And so I'll still have the 40 volume boxes along the fuselage, but then when I interpolate the flow solution back onto the surface panel model, those 4 boxes will get mapped back to 1 surface panel box. So that's allowed, and it can make modeling your body 7 fuselage a little bit easier because you don't have to have so many boxes. So that is allowed, and I do that sometimes. But the easiest rule to follow is just make sure that the lines are always coherent between adjacent body 7 and ZEUS elements. Now, for any two chordwise Y lines whose maximum distance is smaller than a small tolerance, then one of the chordwise Y lines is removed from the mesh. So if we go back to this figure, let's say that these two lines are very close together. They're not exactly the same, but they are very close together. If they're within the small tolerance, ZEUS, after generating the mesh, will go back and then remove one of these lines because it will say, oh, this box is too small to bother with. I'm just going to remove one of these lines. So for example, if it removes the aft line, then when we do the mapping on YZone 2, the computational mesh to the ZEUS, our grid isn't quite coherent. ZEUS will still map the pressures back. That'll be fine. But you do want to avoid this because you're not sure like which line it's going to remove. So it's best just to have the coherent mesh. This is kind of a fail-safe. If the user makes a really poor surface panel model, ZEUS will say, oh, okay, I can't have these two Y lines too close together like that. That'll cause the solver to blow up. Next, the chordwise Y lines ahead of the leading edge of the ZEUS or the nose of the body 7, and behind the trailing edge of the ZEUS or the aft end of the body 7 in the flow field are automatically generated by growing the chordwise Y lines from the wing leading and trailing edges along the upstream and downstream directions to the outer boundary of the block. So for very simple models, you don't need any kind of gap card to control the mesh generation. ZEUS will just automatically grow the mesh from the leading edge all the way out to the boundary, and then it will grow the mesh from the trailing edge out to the boundary here. And so that's why we say ZEUS has this automated mesh generation scheme. In most instances, it's very easy to set up the model, and then ZEUS will just generate the mesh for you. Next, we'll look at the sheared mesh on the XY plane. Let's see slide number 2 here. So the Spanwise X lines on the surface mesh are generated according to the spanwise divisions of each ZEUS, and each spanwise division of the surface mesh generates a spanwise X line. Now for a wing-tail configuration, if the spanwise divisions between the wing and the tail are not aligned with each other, then extra spanwise X lines are generated. So in this example, we have a tail with 3 boxes, so we have 4 cuts, and then we have a wing with 5 cuts and 4 boxes. And you can see that these cuts are aligned with each other. Now over here, we have our 4 cuts for the tail, and then we have 3 boxes, so we have 4 cuts for the wing, but the lines are not aligned with each other. So once again, ZEUS with this line tracing method will create the line here. So we cut this ZEUS in half, and we have the line here. So once again, we're increasing our mesh density without increasing the fidelity of our results in the original surface panel model. So after the Spanwise X lines are generated on the surface mesh, the Spanwise X lines in the flow field are generated by growing from the right and left wingtip to the outer boundary of the block of mesh. So the same thing from the wingtip here, we grow this mesh out to the boundary. And the chordwise Y lines and the Spanwise X lines form a sheared mesh on the XY plane. So next we'll look at the YZ plane. So within each Y zone, a set of horizontal Y lines are first generated by growing the horizontal Y lines from the mean plane of the ZEUS and the top and the bottom surface of the rectangular box of the body 7 along the Z-axis to the outer boundary of the block. And then the connection of these horizontal Y lines between adjacent Y zones is achieved by the line tracing method. So if we look in the case of only a fuselage, ZEUS can automatically generate the entire flow field mesh. We grow from the top of the body box out to the boundary, and we grow from the bottom of the body box out to the boundary, and we get a good mesh. On the other hand, if we have only a wing and we have no fuselage, ZEUS works very well too. It'll grow these lines automatically. Now when you have both a fuselage and a wing, then this automatic mesh growth doesn't work quite as well. ZEUS will create this first line above and below the wing here of this DZ distance, and then it will create this line above and below the body box, but ZEUS doesn't know what to do in the interior here. Outside of the fuselage from the boundary, this growth works just fine. And the same thing at the bottom here, this growth will work fine. But in here, ZEUS doesn't know what to do. So if you have a fuselage and a wing together, then it becomes necessary to additionally create a gap Z card. And you only need one gap Z. And the gap Z will specify where these horizontal Y lines should be. So you could place the gap Z either here, so it's on top of the fuselage, or you could put the gap Z here in the first, the very first inboard ZEUS to specify where these Y lines should be. And the gap Z only needs to go from the boundary of the body box up to the upper boundary of the body box. Now, the grid spacing of the horizontal Y lines near the surface is determined by DZ fact times ref C, where the default DZ fact is 0.01, and then ref C is your reference chord specified in the arrow Z bulk data card. And the growth of the horizontal Y lines from the surface to the outer boundary along the Z axis is accomplished by a growth rate of 1.3. So once we get out here, each additional DZ spacing is just 1.3 times the previous DZ spacing. Now for any two horizontal Y lines whose maximum distance is within a small tolerance, one of the horizontal lines is removed from the mesh. So once again, if we have two ZEUS who don't quite connect to each other, so we generate two different horizontal Y lines, one of the Y lines would get removed. So with a good ZEUS mesh, that should not be happening. And then the spanwise Z lines on the YZ plane are obtained by simply sweeping the spanwise X lines on the XY plane vertically, that is parallel to the Z axis. And the intersection between the horizontal Y lines and the spanwise Z lines forms the mesh on the YZ plane. So to finally get the 3D mesh of the block, the horizontal X lines on the XZ plane are obtained by sweeping the horizontal Y lines on the YZ plane from upstream to downstream. And then the chordwise Z lines are obtained by sweeping the chordwise Y lines on the YZ plane vertically, that is along the Z axis. And the intersection between the horizontal X lines and the chordwise Z lines forms the mesh on the XZ plane. So if we have M number of chordwise Y lines on the XY plane, N number of spanwise X lines on the XY plane, and L number of horizontal Y lines on the YZ plane, then of course the total number of grid points is M times N times L, and the total number of computational cells in the volume block of the mesh is M-1 times N-1 times L-1. And remember, ZEUS uses the cell-centered solver. So we have the M-1 times N-1 times L-1 points at which ZEUS is solving the flow field mesh. Now ZEUS applies the finite volume method to evaluate the influx and outflux of each cell and computes the flow solution at each grid cell center. And after the solution is obtained, ZEUS interpolates the solution at those grid cells near the surface mesh to the centroid of the ZEUS and Body 7 panels. Therefore, the final solution of ZEUS is always presented on the ZEUS and Body 7 panel model. So the computation is done on the volume grid, but then all of the display is done on the surface panel model. So if you have a plot CP card to display the CP contour on your model, of course that's going to display on the surface panel model. And then your aerodynamic load computation is done by integrating the forces on the surface panel boxes. So next we'll need to look at the overset mesh scheme. So the Overset Mesh scheme enables the modeling of complex configurations whose components cannot be fitted into a single block of mesh. And this will happen when you have a configuration that has overlapping components on the projected XY plane or YZ plane. Then those overlapping components must be fitted into different blocks of mesh by specifying multiple block bulk data cards. So here we have a wing, pylon, and store. So when we looked at the projected XY plane, you can see that the store and the wing obviously are overlapping. So it's impossible to put both the store and the wing in the same block of mesh. So what we would do here is the wing would be in our main block of mesh, and then we would take the store and pylons and put those together in a second block of mesh. Furthermore, this second block of mesh, we would rotate it 90 degrees so that this vertical pylon locally in this block would become a horizontal surface. So we have a so then you can think of it as we have the store, and then we have one kind of wing, a horizontal surface sticking out on one side. And then this block would be embedded inside the main block. The second instance here, we have the intersecting wing and vertical tail on the projected YZ plane. So if we look from the back view here, so we're looking at the YZ plane, you can see that the wing and the vertical tail intersect with one another. So once again, these would not fit into the same block of mesh because our vertical Z lines, if we try to fit this tail, either aren't vertical or we would have our Y lines here are intersecting. So that's not allowed. So in this case, the vertical tail must be put into a separate block. And usually the vertical tail, on almost all cases, the vertical tail is going to be going into a separate block anyway. Next, the Overset Mesh scheme first performs a hole cutting procedure in the overlapping regions of the Overset Mesh. So each cell is determined to either be a donor cell or a receiver cell. And the flow solution is computed for all donor cells by the flow solver. And the computation is not performed on the receiver cells. And then interpolation coefficients are computed using a connectivity algorithm to transfer the flow solution from the donor cells to the receiver cells. So if we go back to the store and pylon underneath the wing, the block that contains the store and the pylon will be sitting within this main block. And the outer two layers of blocks in the store block here would be receiver cells from the main block. So the far field boundary condition, essentially, of the store block, which is the inner block, is being interpolated from the main block. And then meanwhile, in the main block, the interior cells that contain the pylon and the store here would be receiver blocks. So the flow solution of these volume blocks that would overlap with the store here are the receiver cells in the main block. So they're receiving the flow solution from the store block. Now, the solution convergence within each time step is achieved by the Newton subiterations. So during each Newton subiteration, the flow solution in each block of mesh is computed independently. The receiver cells are held constant, maintaining the received values from the previous iteration. And then, after each Newton subiteration, the flow communication among the blocks is obtained by interpolating the flow solution in the overlapping regions from the donor cells to the receiver cells. So in this way, you can see that as we converge, the flow will become converged, where the influence from the inner block is seen in the outer block, and the influence of the outer block is seen on the inner block. Now, because of this, the overset mesh should be avoided if all of the components can be fitted into a single block of mesh. So you shouldn't just use overset just because you can. If it's possible to use one main block, then that would be ideal. However, we've shown that sometimes it's impossible, so you must use the overset. But the goal should always be use as few blocks as possible. Now, the interpolation of the flow solution in the overlapping regions may introduce error and reduce the solution accuracy. And additionally, the overset mesh increases the number of grid points and requires the Newton subiterations, which leads to longer computation time. So here's an example of the overset mesh. So here we have 12 blocks of mesh, which are required to model an aircraft with 3 underwing stores. So block 1 consists of the fuselage, the wing, the horizontal tail, the tip launcher, and the strakes. And then block 2 here consists of the underwing tank and the supporting pylon of that tank. Blocks 3 and 4 are the 2 underwing missiles with their respective pylons, but excluding the canards. And then blocks 5 through 8 here consist of the canards and fins for the inboard missile. So this block here, let's call this block 5, that contains both the canard and the fin for this missile. And then blocks 9 through 12 consist of the canards and fins for the outboard missile. The 3 pylons, okay, let's ignore this statement here. The proper way to do this, as I said earlier, is to rotate this block by 90 degrees. So with this block, locally, the Z direction is this way, and then the Y direction is this way. So in that instance, this pylon here is actually a horizontal surface. And then we have the same story for blocks 3 and 4. So the pylons are horizontal surfaces locally in their blocks. The bigger block here provides the solution of the flow variables for the outermost 2 layers of grid cells of the smaller block as its far field boundary condition. So if we look at block 2 here, we don't have the mesh shown here, but you can imagine we have a layer of 2 blocks, or 2 grids, 2 cells here around the boundary. So these 2 cells are the far field boundary condition for block 2. And so the flow solution of the main block is used and interpolated to these outer 2 cells of block 2, and then that will be the far field boundary condition. And the interior of block 2 is actually solved. And then the same thing will work for blocks 3 and 4, and then additionally 5 through 12. Now with block 5, the outer block is actually block 3. So if we look at the outer 2 cells here for block 5, it's interpolating the flow solution from block 3. Let's see, where's our, in the other direction, the hole cuts. Okay, so then in the other direction, if we look at block 2 embedded in the main block, block 2 hole cuts the main block. So if we skip 2 cells and then look at the interior portion of block 2, this interior portion of block 2 will hole cut the main block. So within this region of the main block, these are all receiver cells and the flow solution is not computed. At each Newton subiteration, the solution from block 2 is interpolated back to the main block within these cells, and then that interpolated flow solution of the main block cells is then used and held constant for the next Newton subiteration, so the influence of the store is then seen on the main block. So you can see here that our boundary of these pylon and store blocks butts up against the wing. Now this is important because remember, the main block flow solution is being interpolated to the outer 2 cells, cell boundary of the embedded blocks. Now obviously the flow solution is going to be completely different and not it has no not affiliated with the upper and lower surfaces. So when we're interpolating the main block flow solution to this block 2, we don't want block 2 to go up above the upper surface of the wing, because then the far field boundary condition of block 2 would be seeing the flow above the wing, which is obviously not physically correct. Block 2 should only be seeing the flow below the wing. So we accomplish that by setting the boundary of block 2 right up against the wing. Now, you may ask, what happens at this boundary intersection between the pylon and the wing? This is kind of a special situation, and ZEUS tries to handle it as best it can, and we'll see this later. But essentially, ZEUS does the best it can to try to make sure that the pylon is influencing the block 2 flow solution, and the wing is influencing the main block flow solution. So for modeling purposes, you want this block 2 to come up and touch the wing, and then you want to be far enough away from the body here. This is probably a pretty good size, so that the body, this store body, is influencing the block 2 flow solution, which then can influence the main block solution. Let's see. So the overset mesh scheme requires that the smaller blocks of mesh are embedded in the bigger blocks of mesh, as we've shown here. So we have a very small overlap between blocks 2 and 3. That's okay, because remember, the outer two volume cells of block 2 and the outer two volume cells of block 3 are receiving their flow solution from the main block. And the main block is only hole cut by the interior cells, excluding the outer two boundary cells of blocks 2 and 3. So as long as this overlap is not bigger than 2 cells for both block 2 and block 3, that's okay. Because we can imagine if this is exactly 2 cells on block 2 and it's exactly 2 cells on block 3, blocks 2 and 3 won't be fighting with each other about which cell is donating to the main block. The main block will still exert its influence on the outer 2 cells for both block 2 and block 3, and then block 2 will donate its flow solution to the main block here, and block 3 will donate its flow solution here. However, if in this region we have 10 cells from block 2 and 10 cells from block 3, then essentially they're fighting with each other on which one should donate its flow solution to the main block. So that you want to avoid. So in the same situation here, where we have blocks 5 through 8 overlapping just a little bit, this overlap is not bigger than 2 cells. So that's the key point. Don't overlap these adjacent blocks by more than 2 cells. Now furthermore, usually ZEUS can just figure out on its own which blocks are embedded in other blocks as long as you order them correctly. So the main block would be block number 1, and then we have blocks 2, 3, and 4 are the next level of blocks, and then we have 5 through 8 and 9 through 12. But in this instance, additionally, you want to make use of the block layer card. Now the block layer card tells ZEUS what the layer number is for the blocks. So in this case, the main block is the first layer, so that would be layer 1. Blocks 2, 3, and 4 are layer 2, and then blocks 5 through 8 and 9 through 12 are layer 3. Now when you tell ZEUS about these layer numbers, then ZEUS will know, oh, okay, blocks 2, 3, and 4 are all layer 2, and that means because they're all layer 2, they should not talk to each other. All of the layer 2 blocks are allowed to hole cut the layer 1 block, and the layer 2 blocks are allowed to be hole cut by layer 3 blocks. And then furthermore, the layer 3 blocks will only communicate with the layer 2 blocks. The layer 3 blocks will not talk to each other. So the layer is important, and the sequence number is important. The lower the sequence number, the bigger the block. So once again, the main block would be block 1. So in our block sequence, that would be the first block. And then we have blocks 2, 3, and 4, which are the second layer. And then blocks 5 through 8 and 9 through 12 are layer 3. Next, we have the body fitted mesh for modeling the body. Now in this picture here we have an F-18 fuselage. That's just what was used for this figure. You would not use the body fitted mesh for a complicated F-18 body like this. Normally you would just use the body fitted mesh for a simple missile. So if you're doing like a hypersonic missile, which is actually one of the test cases of ZEUS, the aerodynamics are dominated by the body itself. And it's a very simple cylinder. So that's the type of model you would use this body fitted mesh with. So ZEUS provides an option of using a block 1 instead of the block bulk data card to model the body geometry exactly with an automatically generated body fitted mesh around the body surface. So a 2D O-type of mesh around each body cross-section is generated by solving a Laplace or Poisson equation. And then a final 3D mesh is obtained by smoothly connecting the 2D meshes along the x-axis and extending beyond the leading edge and trailing edge of the body to the outer boundary. So we look at this 3D view. At every X station, we have the 2D O-type of mesh generated, and then we come back and just connect all of those generated 2D planes to have our final 3D mesh. And then you can see the mesh is extended from the nose and the tail out. Now because of this body fitted mesh, the exact boundary condition can be applied on the body surface. However, with the body fitted mesh, it can only be used to model one body 7, and you cannot fit additional components, either other body 7s or other C-Aero 7s, into this block. In that case, you must use the Overset Mesh. So, and we'll see this in a test case. We use a hypersonic missile with 8 fins. So the missile body is the block 1. It's the body fitted mesh. And then we have a different block for each individual fin around their circumference. And then we use the overset for the communication between blocks.